My name's Mike. If you haven't met you before, but yeah, thanks for coming. Didn't think that this day would come, so this is a bit surreal, and I think the way I'm coping with the enormity of this is just kind of viewing it as a fireside chat. So hope you all do as well. Ning, would you?
Sure, yeah. Welcome everybody. It is a surprise to me that so many people. I guess we have a very vibrant, dynamic hydrology program. I know Mike some years ago, 6 years ago, I think, when you were still undergraduate student. More than that? Okay. And in one of the GSA meeting, Mike was at the Michigan Tech and giving some talk about the landslide study there. So I'm there through Jonathan Gott, USGS, my colleague, and we hook up with Mike. Mike is one of the earliest hydrology program. You should be proud of that, and I'm really very glad to get to this point. A couple things I want to talk about Mike is work on the area which actually is very important as part of a hydrological problem, but also very interdisciplinary in nature. Part of the reason is, as you see these slides, is the landslide. And this landslide, particular type of landslide, is due to water. And it's, of course, it's under gravity. How it happened and why, it's been a topic that has been under intensive study, but fully understood. So basically, the water actually is going to make the soil wet. But then it's going to change the stress, the interparticle stress in particular. At some point, it's going to have a failure. So Mike's journey basically is to pursue this, how it happened, how we understand hydrologically, not under saturated condition, but under partially saturated condition, to the degree that where it is going to have a mechanical failure. So that's the part of Mike's journey from the field, eventually focus on the lab to understand under what circumstance the theory is going to fail. So I'm very proud of that. Actually, it's a long journey, but actually it's a very torturous path. So, but I think you will get a reward, like you said, it's surreal. So let's welcome Mike's.
Thank you, Ning. Real quick, Mike. So a couple quick duties as Mike's committee chair. Ning, of course, is his research advisor. For those of you who haven't been to a PhD defense before, the way this works, Mike will give his presentation. We'll have questions from the audience first, and then the public portion of the defense is over. You guys are dismissed, and then the committee asks some questions. Go for it, Mike.
Cool. So the title of my thesis is Field and Laboratory Investigations of Variably Saturated Potential Landslides. It sounds kind of glamorous. Once we get to the math part, the glam will all wear it off, but hopefully you'll get something out of it. So just a general overlook, we'll talk about motivation, the general background of slope stability briefly, and then we'll dig into some a field study that we did at the Oregon Coast Range, and then segue into the laboratory experiments that I finished up with the last two papers for my chapters of my thesis. And then talk briefly about some future implications of the work and the conclusions as well. So landsliding and debris flows are obviously a major problem with steep topography, but as Ning said, areas of ubiquitous rainfall. And it's not restricted to just rainfall, but meteoric infiltration, so that includes snowmelt. So in the US alone, we have an estimated $1 billion damage to associated economic structure yearly. And that unfortunately also results in about 25 to 50 deaths. And that's only in the US. Of course, you can extrapolate those numbers worldwide. And, sorry, excuse me. And you can see failure mechanisms occur abruptly, or, you know, they'll creep over inches over several years, as we observed in I-70 and Slum Gully landslide down in Colorado near Lake City. But they can also occur kind of ubiquitously because of, you know, a building right on top of a cliff. But they also range in size. So here's me as a young sprite in 2007 when I basically started research. And this is poetic in the sense that these tailless piles are a slope failure. But so is the Oso landslide that occurred 2 years ago. And this started out as a little rotational failure on top of this hill slope, but transformed into a deadly mudslide that covered a bunch of houses near the toe of this area. So what causes these slopes to fail? What causes these debris flows to become deadly? And how can we predict them? How can we maybe give an early warning to those people down in the riverbed? So earlier in '87, there was a study that discussed a rainfall duration intensity threshold, which is basically an empirical relationship between the duration of a storm and the intensity. Now, it's useful for timing prediction in that they actually successfully predicted the timing of events during a storm in February 1986. However, it doesn't exactly tell you where or how severe a landslide is going to, become. It's like you have this old Subaru, and you had this old Subaru for 10 years, and you haven't maintained it at all, and you decide one day to go four-wheeling. In the UP, we call it mucking, but you go four-wheeling, and you know that something's going to break, right? So this is an empirical-based assumption. You know from common sense, from your own life story, that your Subaru is going to break. However, what we want to be are more mechanics. We want to know exactly what's going to break, what has the possibility of failing on this car, and we'll maybe leave it to fixing it for some other people. But so here's the story on how we want to be more of a mechanic for landslide prediction. And one of the research goals that I outlined is, in order to improve our predictive methodology, is first we need to optimize the way that we characterize hill slopes. So what I'm showing here is from a seminal study conducted actually nearby our Oregon site, the Mettman Ridge site that some of you are familiar with. And this had something on the order of 240 piezometers in an 860 square meter area. So they made Swiss cheese out of this hill slope. You can't even begin to think about the time and the money that this took to, take this on, right? Another way that we can improve prediction is perhaps find some kind of way to detect and or monitor pre-failure movement in a hill slope. If we are aware of a couple of slopes that are especially susceptible to sliding that might be showing a little crown or something of this sort, and we're able to monitor that, that would help us kind of focus in on these problematic areas. And finally, improve the accuracy of traditional hill slope stability assessments. For instance, classically classically, were assumed to occur where the failure plane, or basically the sliding surface, was under saturated conditions. Excuse me. But recently, failures have been calculated and observed to have occurred as suction gradually decreases near the slip surface, but not necessarily in saturated domain. So these failures occur under unsaturated conditions. So therefore, we have to rethink the way that we're going to assess some of these hill slopes that might be potentially problematic. So let's go back to Physics 101. You're sitting in class and you're working on the stupid inclined plane problems. I didn't think they were stupid. I liked them. That's my favorite. So you want to draw your force diagrams with me. So you have the weight of that box, and you separate the components of that weight into your cosine and your sine. So your cosine is your weight of that box in the direction of your inclined plane, orthogonal. And your sine, or your shear force, is that force in the direction down that inclined plane. Now, as a result, we have what's called a normal force of the inclined plane pushing back on that box orthogonally. And what are we missing? We have one more. Sorry, I'm a teacher now, guys. Friction, exactly. So friction is a function of this normal force. And what about this is going to apply to the soils and slope stability? It's exactly the friction and the stresses that occur in this interface between the box and the inclined plane. So if you take sort of a closer look at this, the state of stress at this failure plane depends on mainly two things: the weight of that overlying soil and the moisture content around that failure plane. And so what we use in soil mechanics is factor of safety, basically just the sum of resisting forces ratioed over the shear forces. And if we have a factor of safety of over unity, then that box is staying still. But we don't want that box to move. So ways we can get that box to move are adding moisture content typically, and also adding weight. So the depth to that interface also matters in the sense that we could have basically a bathtub effect, right? If you imagine back to your inclined plane problem where you have the effect of friction, what happens when you have minimal friction? That box is sliding. If you have, if you have a layer of goop on that inclined plane, that box is sliding, right? And that typically happens when the soil and bedrock contact that contact between the soil and the bedrock is abrupt. So you might have a gradation of soil changing into a granite, for instance. So before we get into too much of the mathy stuff, let's step back, and we can actually accomplish one of our goals here just by this concept, in that the estimation of variability of soil thickness in a drainage area is really, it's essential for understanding the conditions that might lead to a shallow slope failure. So revisiting Montgomery et al.'s project in Mentman Ridge, this is arguably an intrusive tool for studying landslides, right? You have 240 holes on this hillslope. You arguably could be making, preferential flow paths, right? I think that's contended, but however, what if we can make a less intrusive tool and we can use it adequately and efficiently enough to measure soil depth throughout a drainage basin that's relatively non-intrusive, right? So again, this goes with our first goal of optimizing hillslope characterization in the hillslope. So what I like is DC resistivity, and that's what I did my first project on out in Lake Michigan Bluffs. So I like to revisit every once in a while. So we were considering using DC resistivity to look at soil depths in a drainage basin. Great thing about resistivity is cheap. If you have a box, a DC resistivity meter, it's typically expensive. There's like a little overhead cost. Maybe NSF can take care of that, but after that, it's relatively cheap to go out and do a survey. And you can also take hundreds or thousands of measurements in a span of minutes or hours over a ginormous area. And it's non-intrusive. You might hurt something that would be standing next to an electrode after you're inducing a current, but in terms of damaging your field study, yeah, you're good to go. However, point measurements can be arguably not as cheap, right? Especially if you have a drilling rig required for your operation. And it is arguably slower than taking more like tens of measurements maximum in a span of hours. And it's arguably intrusive when you're using it on Montgomery type scales. So a DC resistivity survey was used in this study at the Oregon field site, which is a small catchment area that I'll show you in a bit. And we compared the accuracy of this resistivity survey to point measurements to see if it's a viable method. So introducing the field site, we're up here in the Oregon Coast Range in the middle of Elliott State Forest. And we're about 20 kilometers southeast of Reedsport, Oregon. And the reason this site was chosen was due to its susceptibility to landsliding. It's generally steep topography, ubiquitous rainfall, very wet climate, and there's also a lot of timber harvesting going on up there. So when you have a lot of timber harvesting occurring, you're cutting down trees, you're introducing more direct precipitation contact with that prospective landslide, and you're also taking away root cohesion. So in our particular site area, as you can see here, is a zero order cage catchment, meaning that the local ridge is on top, so there's nothing above us. And they recently, according to the time of this study, clear cut this area as well. So within a couple of years, we could be in the golden zone for finding, seeing an occurrence of a landslide in our spot here. So, and this little outline is the region specifically where we were traipsing around this hill slope. So the first thing we did in the study was conducted a soil depth point measurement survey. And we, meaning myself, Jonathan Gott, Murat Kaya, who's not here today, and Bashak Center Kaya, she is here. Thanks for coming. So a little more description of this slope area. It was just ravaged with, or it was covered in vegetation, rhododendrons, dug fir saplings, tree stumps, woody debris. It's steep, it's up to 40 degrees steep, and there's scat all over the place. It's hellish terrain to get around. So what we ended up doing, we dug some soil pits, as I'll talk about in a bit. And this is just your general profile of your subsurface that we observed in this field site. So there is this layer of duff and dead roots, approximately 20 centimeters deep on top, followed by a brown cobbly sand that grades to a lighter color as it increases with larger clasts, probably from the weathered sandstone below. So below the cobbly sand layer, we get to more tan weathered sandstone until we reach the bedrock content. So all the pits weren't typically like this. There were some that looked like former slide events, where this is all just jumbled up, a haberdashery of rocks and soil, and there's a big stick down there. How'd that get there? But or nasty buried tree roots that eat soil probes that you try to pull them out for hours on end. So the suite of our soil point measurements included measurements by hand auger, just a simple soil probe, a geoprobe sampler, which is this machine here that Murat is skillfully operating, and hand dug soil pits. This is Jeff Coe from the USGS. He is a machine at digging soil pits, and also instrumented a lot of these pits, which Ben Mears, sitting here, he's looking at a lot of the data and doing follow-up studies on all these measurements. This is all being collected in real time and broadcasted to the USGS website. Still? So this was the result of our soil measurement survey. So this was the map that was created from the soil depths. So, going towards the northeast, that's the direction of the top of the ridge. And as we're going to the southwest, we're going down axis of this drainage basin. So as we're following these transects from B to B prime and A to A prime, we're basically going down and coming back up. So we have a nose here and a nose here, and then we have a converging area right here. So what to get from this plot showing that our soil depth varied in thickness from 3.1 to 0.55 meters. And of course, you can locate that 3.1 just fine, right? But our lower soil depths were associated with the locations on the eastern and western noses. We also extracted near saturated cores with our geoprobe sampler near the GP3 point at 3.1 meters depth. So that's something to keep in mind. Next, we went around and did our DC resistivity survey. So for you resistivity nerds, we did the Winter Alpha electrode array, which is constant spacing between all the electrodes. And the method was selected because it's well suited for locating horizontal layers, meaning that horizontal layers laterally contiguous under your feet. So that's what we're looking for. We're looking for a soil bedrock boundary. And the spacing was 0.7 across the basin axis and 1.0 down basin axis. And this is intended to maximize the measurements around the area of that contact. So one thing I'd like to mention is that the point measurement survey also helped dictate where we would conduct our resistivity survey. So that's something to keep in mind. We can't totally issue soil, or we can't rule out point measurements quite yet. And here's Bashak helping out. This is quite a lovely picture, I thought. So as a result, we had 3 transects for the geophysics. From A to A prime, going approximately 98 meters in length. From B to B prime, approximately 67 meters in length. Both of those are the upslope and downslope transects, respectively, and they're going from nose to nose. And then finally, the last transect, C to C prime, that goes down the axis or down the ditch, if you will, and that extends about 80 meters. So this is still the soil measurement map, so as not to be confused. I'm just using it to show you the transect locations. So as a result, we got our geophysical pseudo sections, as they're called, which basically they're non-unique solutions, right? We have a distribution of resistivity, as you can see here, where the red splotches indicate areas of relatively high resistivity, and the blue indicate areas of relatively low resistivity. What does this tell us? Well, we don't know yet, right? What is it going to look like around our soil bedrock contact? So this is what Jonathan likes to call geowizardry. So what we have to do is make measurements of our soil and bedrock hydroelectric properties. So specifically, we took soil samples from the field site, compacted them to a homogeneous porosity, and mixed them to a range of saturations. And then we measured that resistivity. Similarly, we took a sandstone sample. That was far more fun because you measure porosity by buoyancy test, chisel it into a nice block shape. And we had to do all kinds of fun stuff to reap the resistivity distribution out of that sandstone. And as a result, we see here a change in resistivity over as we're applying different degrees of saturation. And so what we generalized was the material properties for a saturation of about 50%. For the soil, about 3,000 ohm meter, and bedrock about 1,250 ohm meter. So that follows along that line there. So how can this be useful to really interpreting the resistivity fields? So we input this data into a forward model. So I basically chugged all of everything that we've looked at so far, the measured values from the laboratory testing, the topography for each transect, and again, soil point measurements. So we know exactly where that depth of the soil bedrock contact is. And we can see here with the forward modeling that we see around the area of the actual contact, this change between the yellow and the orange resistivity contours, which are roughly around 2,000 ohm meters. So it's on this basis that we locate the soil bedrock contact. They're also laterally extensive, which is also indicative of a contact. So if we apply this, this finding to our geophysical data set, now we don't have so much of a non-unique solution anymore. Now we can apply this here where we see similar laterally extensive trends with orange and yellow contours around the 2,000 ohm meter mark. And so this is for the A to A prime and B to B prime going up and down the noses for the upslope and the downslope resistivity transects. So just little things to point out here and there, we're seeing these large or relatively high resistivity anomalies, and it's decreasing in depth. So if we look at the down axis transect from C to C prime, we see very similar anomalies near the top of relatively high resistivities, and it decreases in depth again. But we also see this laterally continuous sort of feature here around the 2,000 ohm meter mark. So this is what we used with all of our transects to interpret soil depths throughout this entire drainage basin. And as a result, this plot was generated, and it was also used geostatistics to create this plot to give it more of a two-dimensional feel, right? So that we just don't have soil depths along these lines. We're also interpreting between the lines. So that's an important thing to keep in mind. So ultimately, we're going to compare, or in comparing this resistivity interpreted plot with the soil depths, they compare quite well, right? We see this relatively large soil depth near the bottom of the axis transect, similar to here. We also see a general decrease in soil depth as we're approaching each nose on the landscape. So a few limitations that the decrease in measurements decrease in accuracy, or your predictions in soil depth decrease in accuracy away from the transect lines. They also decrease in accuracy down drainage access, so further down here. So what I'm showing here is the depth difference between the resistivity data set and the soil probes. So this is basically the error plot, right? And we see significantly more error towards the lower end of the axis transect. And I think this more had to do with anomalies from slide occurrences. So former landslides that brought soil down to this area and kind of jumbled up the material as it went. So as a result, we also had an RMSE of 27 centimeters compared to the ground truth measurements, which it's not too bad, I think. So in conclusion, we use these DC resistivity surveys to map soil depth, and using a combined effort of soil point measurements, laboratory material properties measurements, and forward modeling, we made these interpretations. So these are essential for piggybacking on the DC effort. And also these depths were interpreted to root mean square error of 27 centimeters. So I think it's a reasonable assumption to make that the DC resistivity method can adequately measure soil depths throughout a drainage area. You have some small characterizations efforts here and there, but I mean, do this study, then poke 300 holes in the ground. I guess it's up to you. So, and finally, as a final conclusion, we had a good solid crew out there, a good week. So that was all of us working out there. A lot of USGS and school mines folks. So back to our box. You remember our box? So if we go look back at that interface where we have the effects on how that box is going to move, again, we describe what might affect the weight of the overlying soil, right? Your soil depth, but also moisture content. So I know you hydrologists in the room have been jonesing for some hydrology, so now you're going to get it. Going back to the factor of safety analysis, in soil mechanics, we like to convert things to stress. Oh, that didn't show up. So this is supposed to be, so at factor of safety in soil mechanics, we say the shear strength over the shear stress instead of resisting forces over shear forces, but it's really just force over unit area, so we're just dividing by unit area. So don't be too frightened about it. But anyways, what I'm trying to accentuate here is the importance of shear strength, which is just basis for the resisting forces. And shear strength really relies on this factor here, which is called the effective stress. So what influences effective stress? Well, Terzaghi back during World War II came up with his effective stress for saturated conditions. And basically, your effective stress will decrease with increasing pore moisture content. Simple enough, right? And it's still used to this day, and it's widely regarded as the basis for a lot of these analyses. However, for unsaturated conditions, it's not so straightforward, right? So you have a contribution of two main forces. There are others in there, but mainly it's gravity and it's suction. So how do we have marriage between these two tell us how it's going to affect effective stress? So Liu and Lycos proposed actually a suction stress term as a function of effective saturation and matrix suction. Some of you already know where I'm going to go with this later, but there are other things that are a function of saturation and matrix suction. So generally, it's suction stress, sigma S, as a function of those two. Extended off Bishop's effective stress for unsaturated soils gives you a nice tidy relationship. How effective stress changes with the suction stress quantity, which you can conceptualize not so much as a nebulous variable, but a sum of the active forces near the interparticle contacts in the soil. And it results in a tensile, meaning that it likes to hold things together. So it's a negative quantity. So yeah, now we have a nice neat little unsaturated assessment using Liu and Lycos' extension of the Bishop's effective stress. Now, how do we quantify this in a better way? This actually works very well with Van Genupten's soil water characteristic curve. So as you see to the right here, according to Van Genupten's relationship, as saturation increases, your matrix suction potential in your soil pores increases dramatically for several different soils. So this depends on soil, it depends on the state of wetting with soil hysteresis, whether the soil is being wetted or is drying at the moment. And so if we combine Van de Geneuchten's original model with the suction stress term, then we can formulate suction stress characteristic curves based on Van de Geneuchten's soil water characteristic curves. So this is immensely powerful in that for a given saturation, you can assume a suction stress based on if you know the soil properties and if you know whether it's in a state of wetting or dry. Again, this is unique for wetting or drying cases with hysteretic soils. And so ultimately you can go build sandcastles with what you just learned. Well, going back to that, so this applies directly to this research because you're sitting at the beach, right? And you want to make these large towers. What do? You add moisture content, right? Typically. So let's look at the suction stress curve here. As we're adding moisture content, we reach kind of an apex or a maximum in the soil stress. Well, what happens when you add too much soil moisture content to your sandcastle? It turns into mush, same as here. As you're increasing saturation for a sand, you're essentially turning it into mush and decreasing that suction stress to 0, which is essentially what happens in some cases at the shear zone of some landslides. So I got a little bit ahead of myself, but again, going back to the box, how does this apply to strength and soil stability, or slope stability, excuse me. So going back to our original shear equation, in saturated cases, effective stress will decrease with increased water content. However, in unsaturated cases, effective stress will increase or decrease depending on your wetting or drying path and where you're at in the soil water characteristic curve. If you're near saturation, your effective stress might decrease from that maximum value that I showed you earlier. So let's kind of apply these concepts to an aging method. So this is, what we'll talk about is Kalman's method. And of course, this was formulated just on the tail end of the Civil War and is still being used to this day. So essentially what it asks is, to what height can a cut slope be constructed where the slope becomes critical and fails? And this is denoted as the critical height of the cut slope. So the critical height is figured by this equation. And what I'd like to point out in particular is this cohesion term. So there are limitations on this, of course, being a 150-year-old theory, in that it's applied to two-dimensional cross-sections of slope. And this term, apparent cohesion, is essentially 0 for certain unsaturated soils according to soil mechanics. So this takes sands out of it, and certain silts, and some sandier loams. So but you know when building your sandcastle that you can construct a slope like this with unsaturated sand, right? So something in this model is not particularly jiving. So I think that using the suction stress concept, we can extend Kalman's original method to unsaturated soils, and we can add that third dimension in there as, while we're at it. So this applies to the second and third goals of what I think would help with landslide prediction and efforts, in that we'll get to goal 2 in a second, how we'll get to detecting and monitoring pre-failure movement. But of course, this applies to improving accuracy of hill slope stability measurements. So this study was published in 2014, and we also just finished a paper that's going to be submitted soon, hopefully, to the same journal as an extension of this work. So as a summary of this work, Kalman's analysis was extended to unsaturated soils, like I hypothesized. And this extended vertical cut theory, which I'll talk about in a minute, also proved better at comparing measured slope heights when taking into account the third dimension. Now we're back slow. How do we get to this extended theory? So looking at a conceptual model of a three-dimensional cut slope, basically just a block of cheese, but imagine that block of cheese being sand. So there's Kalman's original method, right, from 1866. Simply, if we apply the suction stress term to to replace the apparent cohesion, since apparent cohesion is a function of suction stress, as outlined in Liu and Lykos 2006, we can directly just toss that guy in there, do a little bit of trig on this part, and boom, we have extended Kuhlmann's theory to unsaturated soils. Yeah, easy enough, right? So let's take that step further. Let's extend it again to the third dimension. So now we have Kuhlmann's method with the suction stress variable. And we do some trig fun. I'm not going to derive this equation. It's not going to be all handouts for you guys. It's actually kind of a nightmare, so you can go see it on the paper. But essentially what this spits out is an extension to three-dimensional slopes. But unofficially, I like to call it the Morse equation. Henceforth. My trap. You know, it's a little bit messy, but it's not too bad when you take apart all the variables. And
You're prepared to derive that flux later, right?
yeah, I actually have pictures, so I'll just follow along. So basically, how this is extended to 3 dimensions is you add 2 other failure planes along the sidewalls of this block of sand. There it is. The secret's out. So how do we reconcile this theory? How do we basically prove that it's okay? Well, first we'll non-trivially build a vertical cut failure simulator in the laboratory to test the theory, of course. Which basically, this vertical cut simulator is a glorified aquarium with one sliding door on one side. So you start out with your box of sand, essentially, mixed to a moisture content, and then you gradually remove this sliding door, sliding trap door, if you will, until the slope fails. Boom, you have your critical height at your given soil porosity and moisture conditions. So actually, what I'm showing here is a failure surface after the sliding door was removed sufficiently to create a failure or have a critical height. And I'm just taking soil moisture measurements too. So again, if we take apart this equation and test for all the soil shear strength properties and soil water properties included in Morse equation, then we can account for everything here, right? So this table shows the result of all our testing methods, including dry direct shear tests to get our internal friction angle, inclined plane friction angle testing apparatus, which I invented based on some other previous work, and that's to get soil water friction angle. Basically, it's just a crank and a glass surface, and you crank the glass surface until it slides off of it, But it's rigorous. And then finally, flow cell or axis translation tests that are being used constantly in the geotechnical lab over in Brown Building. And this is how we get our Van Genupten parameters, as well as our saturated residual moisture contents. Quite nicely, actually, compared to Tempe cell measurements, which might take on the order of months. This takes on the order of hours. So as a result, we're able to formulate our own soil water characteristic curve and suction stress characteristic curve based on the equations I showed you earlier. So these are the curves for the soil that was used in these experiments. And as you can see here, it has a similar kind of trend as we looked at with the sandcastle example, right? Where it increases to about a maximum and then drops off as you get to a degree of saturation of unity. So within this regime is where we tested the extended Kuhlmann's theory. So specifically between saturation levels of 0.05 and 0.1. And the reason this area was used is that this provides enough suction stress to hold things together, but not enough water content to drive gravity-driven drainage of the water down into the block, basically. So it's a nice little band there. So step 3, what I ended up doing was taking 2 digital cameras and took concurrent photos of the sidewalls or the XZ plane, the side view that we'll call it, and the plan view, or the top view on top. And this was to try to figure out where exactly is this slope deforming prior to abrupt failure. So we're going to test you guys' eyes. The old people in the audience, I'm sorry, but we're going to play a game called Where's the Deformation? I'm going to show you a suite of pictures, and I want you to figure out where exactly the failure plane is going to propagate from. You ready? So this is at a slope height, or a shear face height of 0. Now we're going to remove that door, and that height is 7 centimeters. Now we're going to extend it again to 10. And we'll extend it one more time to 13. And then finally, boom, we get a failure at 13.3 centimeters, which is our critical height. Did you guys see? Did that agree with what you thought was going to be the failure plane? Let's look at it again. Yeah, you can kind of see it right there, right? Can you quantify it? No. This is why we use what's called particle image velocimetry, which has been around for a couple of decades, but actually longer before that. And this is typically used for particle tracking of floating in flowing media. And a nice natural analog to this is looking at algal formations on a pond. You know, sometimes they're arranged in a very convoluted manner, but that just shows kind of the eddies and, you know, the wind-driven kind of ripple effects from the pond. And, you know, that's a function of how the water is flowing, right? You might not be able to see the water flowing because it flows so slowly, but your algae is going to indicate the direction of flow. So we're using this for geotechnical applications as applied by White et al. And one of the co-authors on this work, Andy Tate at Queen's University, he helped formulate this MATLAB module. So he's one of the big chiefs behind this method. And it's really capable of detecting displacements as small as 0.05 millimeters. So I don't know if you can see that in high resolution. I'd be impressed, but we apply this to a grid. So for example, we're looking at the sidewall view here and the top view here. So with our PIV experiments, the first thing we do is take that reference image. So we did that in the first step of our little game that we played, right? At h equals 0. The sliding door was slid downwards every 0.5 centimeters, thereabouts, and then the photo is taken. We repeat, and the experiment progresses as we did until abrupt failure occurs. Now, the images are processed for PIV placements after the fact. So grids in the XZ and the XY planes are defined at that point. And then images, finally, for each door increment are compared to the reference image, so that from the reference point, each of these boxes kind of looks at the grains of sand, specifically the darker grains. And for instance, at a slope height of 10 centimeters, we get a vector. So that's just the difference in location of that little box of sand grains from the reference image to this image taken at 10 centimeters of slope height extension. So this is the plot shown for the top view of the cut slope, and this is a plot shown for the side view. So as we can see, we have movement in the location down and to the right towards the sliding door, and also down chiefly in the direction of movement of the sliding door. Similarly, we have the top of our soil volume moving towards the sliding door as the experiment progresses. And we can see that clearly. And here's a handy little flow chart showing how the experiments each progressed. So again, let's go back to the picture taken at 10 centimeters. We can superimpose this plot on top of this soil volume, showing you precisely where each of these grains, how they moved, how far they've moved over the course of this experiment compared to the reference image. So it's a time-lapse deformation tool. So you can make handy little contour plots from the displacement data. And what I'm showing here is the same experiment that failed at 13.3 centimeters and had a moisture content, volumetric moisture content of 0.029. So as you can see here, as the door is being slid in the side view, we have maximum displacement towards the top right corner of that cut slope, which is what you might expect. Then let's look at the top view. For the top view, as our experiment progresses towards failure, we have increasing magnitudes of displacement, but we're also seeing smaller changes in displacement as we're going, we're seeing this area right here. So what you can do with this plot, or what you can do with this data here, is take the first derivative in the direction of the sliding door, and that results in a strain. And strains are what we look at with stress-strain relationships often in soil mechanics. So what is plotted here is the strain in the x direction, or the direction of the sliding door. And this is just before failure at that 13 centimeters mark. So as you can see here, we have strains of just over 2.5%, right? Because it's distance towards the door divided by total displacement. So it's a percentage or a ratio. And they can be calculated from any of these displacement fields. So now what I plotted here was the approximate location of that failure plane. And what you can see right off the bat is that is very coincident with the area of maximum strain localization that we calculated from the PIV data. And if we superimpose that on the top view of our soil volume, at that point in time, we can basically make an assumption that this will be the future slope failure crown, right? So let's bring this puppy to failure. That's about where it was. So now we have a tool that can feasibly be used for predicting where a landslide might occur. So we conducted this over a suite of experiments, and these were all strain calculations immediately prior to failure. So it wasn't just unique in that one sense. As you can see, it gets sort of off in some places, but generally they're apparent at the relatively around the location of the eventual failure plane. So if we bring this back and compare it to the Morse equation again, we see an agreement with the sidewall correction, that's the Morse equation, of about 22% error. This is compared to Coleman's method using the suction stress term, where it had approximately 88.5% failure. So this tells us right off the bat that we need to take into account three-dimensional effects in some laboratory experiments conducted with unsaturated soils. So as general conclusions of this study, Coleman's method was extended to unsaturated soils, like I showed in the beginning, and we used a vertical cut simulator to test this theory. And the PIV tool was similarly used, well, it was used in conjunction with this experiment to try to delineate that failure surface as each experiment progressed. And finally, we got about a 22% error, which is quite agreeable with using the Morse equation or extended theory. So as a latch on to that study, we are also testing the influence of or basically the bounds of that influence of the third dimension. So in our most recent work, and I'm getting long-winded, so I'm going to wrap up quickly. But in our most recent work, we basically took those sidewalls and extended them to three different distances to test a theoretical relationship between sidewall width and critical height. Now, according to the extended cut theory, we'll reach as we're extending sidewall width, it's not going to affect critical height as much when it reaches asymptotic. This relationship gets to asymptote. And that means that essentially we're going to be looking at a two-dimensional problem, or local failures might occur in the slope. So just real briefly, what we did was conducted these experiments and plotted them on this theoretical curve. And what we see here is that they generally agree. So I think more experiments needed to be done to kind of delineate this part of the curve, but mechanisms that we observed in these experiments also suggested that local failures occurred, and we have some different failure shapes that I didn't propose or didn't show on here today, so I wanted to get through, but different failure shapes showing different failure mechanisms possibly. So what we're seeing here as we're getting into higher sidewall widths, possibly different failure mechanisms. And furthermore, as a result of these experiments, we had a mean error of about 14% compared to the experimental, or compared to the extended vertical cut theory, which just means that I'm getting better at experimenting. So a future direction of this work is that the PIV tool is not scale limited, right? You can feasibly take this outside and point a camera at that hill slope over there for a series of months and do a similar study, right? People do this with the extreme ice surveys all the time. You've seen this at the airports and whatnot. So I think this tool is ready to use for more rigorous geotechnical applications where this could tell us exactly where a failure might occur and maybe prevent some things like this that happened in the Bingham Canyon mine in Utah. It's a gorgeous picture, and luckily anybody was hurt in this, right? Amazingly. So that's one direction I see, is one future direction I see from the PIV tool. So let's step back for a second and look at our goals for becoming a better landslide predictor, right? The first, we optimized hill slope characterization methods using the DC resistivity method, right? We did this in the first study that we looked at, the Oregon Coast Range, and the study was published where we measured soil depths using a resistivity survey instead of a ton of soil measurements, or soil depth point measurements. Secondly, we detected and monitored pre-failure movement in susceptible slopes. And we did this using the PIV tool that we just looked at. And then finally, we can arguably say that we improved the accuracy of the Kalman's method by extending it to suction stress and extending it to account for three-dimensional forces. So that's a hat trick, I think. Yeah, so that pretty much sums up what some of the work I've done, at least. I just want to go ahead and acknowledge several people. First of all, Dr. Ning Liu and Dr. Gott, who were my co-advisors and were infinitely patient with me and saw me through a lot. Reed, Maxwell, and John Gray, who didn't seem to pull out whatever he was doing. But he usually has a minute for you whenever you need. John and Reed both. Thanks, Reed, for giving me a job. Andre Revelle, who also couldn't be here today, but he helped significantly in the first portion of the research efforts. And Dr. Alexandra Wayless. And I gotta call Alex out here. I don't think any of this would ever finished if it wasn't for Alex. Because she is one who will stay in the lab until midnight for anybody in the group, multiple days a week, to make sure that something goes right and that you don't break anything. Which I tended to do a lot, but mostly she was there to help you out. So I can't thank Alex enough for being there for me. And then some faculty, Kamini and Dave, you're always there. Your doors are open. Same with Paul. And Unsaturated Soils group, we had a lot of members over the years. Some I got to work more closely than others. Yidong, he's here today. We had a good time in North Carolina. And Wan Lee, yeah, it helped me out a lot with the camera stuff. And Jinga Wang, he's in China right now. He's the guy manning the total station there, but he helped a lot with the strength measurements and soil water measurements for the PIV and the extended theory. And I'm going to single out the Kayas. Bashak couldn't make it, but her husband Marat wasn't here. But basically, my first few years here, they kept my factor of safety above 1. So my hat's off to you guys. Yeah, I can't thank you enough. And then a slew of friends, my family, all you guys who can make it out here today, Dr. Ted, of course, and everyone who made food, and you guys who listened to my talk last night. And Maxwell Research Group, I wanted to point out too, with a ton of you made it out today, which is great. So with that, I'll take any questions. So.
Awesome. So I'll let Mike field his own questions from the committee.
Yeah, Mike.
Yes, so you addressed my main question, it's the scalability of your results. But the lab experiments use PIV, which is typically used for small scale fine resolution measurements, right?
Right.
So in the field, what kind of technology would you use to measure those velocities and predict things like?
So the measurement power, if you will, in the laboratory is based on your camera system that you use. So in the field, you might not get to that fine a resolution of 0.05 millimeters per se, but you would still use a very similar setup, I would imagine, with a some kind of high resolution camera or video camera. And it depends on how far away you can get or how close you can get to the slope. If you can get within a few meters, then you can have ultimately the lab scale resolution out in the field. But say if you're observing from across a valley from half mile away, then you're not going to see that kind of resolution. So it's based on your equipment and how far you can observe from.
What's your fancy camera for the slow slide?
Fancy, oh yeah, they're like baseline Nikons that we use, some the DS